Hi everyone. Today we're going to start with networking, and in today's video we'll learn about OSI layer, and in the subsequent videos we'll discuss different HTTP versions, what are the improvement each HTTP version came up with. We'll discuss about important network protocols, when and why we should use them and when and why we should not use them. We'll take an example and see how DNS resolution works. So let's get started today with OSI layer. So what is an OSI layer? OSI layer is basically a set of guidelines or rules set up by ISO, that is International Organization for Standardization, for communication between different devices in a network. So let's say we have two computers, one is running on Mac OS or Linux and the other one is running on Windows, and they want to communicate with each other. So since they're running on different operating system and they understand different language, it becomes difficult for them to communicate with each other. So this is where OSI layers come in play, which provides a standardization for communication between these devices which are running on different operating systems. So OSI layers basically consists of 7 layers, starting with physical layer, data link layer, network layer, transport layer, sessions layer, presentation layer, application layer. So when the sender wants to send the data travels all the way from application layer to physical layer, where the data is encapsulated. That is, the data is encrypted, serialized, and broken down into smaller pieces, smaller chunks, and so that they can be reliably sent over the network. And once the receiver receives the data, these smaller chunks, they travel all the way from physical layer to application layer, where the data is decapsulated, wherein the data is reassembled and basically decrypted and deserialized, so that they can be formed again in a human readable format. So let's deep dive into application layer and see how it works and what it does. So in the application layer, basically application layer consists of a set of protocols, okay, and the network applications that we have, which is basically your web browser, that is like your Firefox or Chrome, or your client-side applications such as WhatsApp or Skype or web apps that run on these browsers. So all these network applications, they will use these protocols that are a part of application layer to transfer the data on the internet. Okay, so these network applications themselves are not part of application layer. They are sitting outside of application layer, but they will use these application layer protocols to send the data further on the internet. So let's understand that with the help of an example. Let's say if you want to send a parcel, and let's say you want to send some consumables inside that parcel. So you will package it inside a airtight sealed containers, right? If you want to send some clothes or let's say some books, you will use carton boxes. And if you want to send letters, you will use envelope. So for each of the different items, right, we use different packaging materials. So in a similar way, these protocols, they are tailored to facilitate different types of communication to send different types of data over the internet. So let's see, HTTP and HTTPS, they will be used basically for during the web surfing, and SMTP and IMAP will be used for email based communications, to send emails on the internet. And FTP and SFTP, basically these are like file transfer protocols that will be used to transfer file. And we have SSH and Telnet that will be used in virtual terminals when you want to control remote desktops or remote servers. Okay, now in the application layer, DNS resolution also happens. So what is DNS resolution? So when you, let's say, type in google.com on your browser, right? So on the internet, every server will have a identifier, and these identifiers are called IPv4 or IPv6 addresses. Okay, now the internet does not know what google.com is. They will only identify each of these servers with the help of IPv4 and IPv6 addresses. So when you type in google.com, your browser will go and check whether they have the IPv4 and IPv6 address for Google browser or Google servers. If they do not have it cached already, what they will do is they will go to the internet service providers and they will make recursive calls by the application layer itself. Like in the application layer itself, they will make recursive calls using the OSI models to get the IPv4 and IPv6 addresses from your internet service provider. And once they have these IPv4 and IPv6 address, they will use this IPv4, IPv6 address to communicate further to those servers on the internet. Okay, so this whole process happens in the application layer. Now, user authentication and user authorization also happens in the application layer. So what is authentication? Authentication is where a user correctly identifies himself. Okay, and what is authorization? So authorization is a process when the user has already, let's say, authenticated. The servers will tell what are, based on the permissions that the user has, what are the resources this particular user is authorized to use. So based on whether he's an admin or whether he's a common user, he'll be authorized different resources. Okay, so let's say you logged in into google.com. Okay, so once you log in, all the subsequent requests you do not need to log in again, right? So once you've already logged in, all the subsequent requests you do not need to log in, and this is where your cached cookies or JWT tokens would be used in the subsequent request, so that the servers know that the user has already authenticated. So one thing that there's a common misconception that authentication and authorization happens in TLS layers. So that is your presentation layer or the sessions layer. So this is partially true. All the TLS based communications wherein you authenticate your servers and the clients, that happens in the sessions layer and the presentation layer, but your user authentication and authorization happens in the application layer. So what do we mean by TLS based authentication, server based authentication? So let's say your computer, if it wants to make a communication to google.com, Google servers, so it might happen that some proxy servers are lying in the middle between you and Google, and it tries to imitate as google.com or Google servers. So it might ask for the password, and you will give the password, and it will cache the password, and then you do not really know whom you are talking to. So this is where this is where your TLS authentication comes in play, wherein the computer, that is your client computer, will basically ask the google.com to send its public certificates, and based on the certificate authority, it will verify whether you are actually google.com, you're claiming as google.com, and that is where your two-way handshake happens and the TLS authentication happens, and you correctly authenticate the service. So this whole authentication actually happens in the sessions layer or presentations layer, but the user authentication and authorization is a part of applications layer. So let's now go on to the presentation layer. The presentation layer has primarily three responsibilities: data translation, data encryption, and data compression. So let's understand as to what happens with the data in each one of them and why they are important. Now let's say we have a computer and we have a server, and your computer understands only ASCII format, whereas the server only understands EBCDIC format. Okay, so when you're sending the data, it will be difficult for the other computer to understand this data, right? So what happens is, in the presentation layer, there is a mutually agreed format that these both computers will agree upon. Let's call that UTF-8, which is widely accepted nowadays. So in the presentation layer, all the data that is being sent will be converted in UTF-8, and while it is being decapsulated at the other end, at the receiver's end, this UTF-8 will be again converted back into EBCDIC format in the presentation layer itself, right? So both the computers can understand each other's communications. Now, coming to data encryption, why data encryption is required. So let's say you're sending a data. Let's say you have a computer and you're sending a data. Now, anyone can tap on the wire and listen on this data unless and until this data is encrypted. So when you kind of convert the data, translate the data from ASCII to UTF-8, you are just doing the encoding. So this encoding does not provide any security. Okay, this just translates the data from one language to the other. So anyone who understands both the languages will be easily able to decode your data, and your data is compromised. Now, to protect your data, what the computer does is shares a symmetric key. So symmetric key 1 and symmetric key 1 will be shared with both the computers while they are doing the handshake on TLS, and this symmetric key will be used to encrypt your data, okay, in the presentation layer. So all this data now flowing on the wire is encrypted with the help of the symmetric key, and only these two computers on the whole of internet will be having this symmetric key. So nobody else can decrypt the data. And in the presentation layer, the servers will basically encapsulate the data, and they will decrypt the data in the presentation layer itself. Okay. Now, data compression. During data compression, your data is basically compressed. The compression can be again lossy or lossless. During lossy compressions, what will happen is you will lose some amount of information. You may or may not lose some amount of information. And lossless ensures that your data is not lost, like none of the data is lost. So lossy, you will generally use lossy compressions. You will generally use while you are live streaming or doing a video call or an audio call, wherein you afford to you can afford to lose some amount of your data. Whereas during a lossless compression, you do not lose any data. So this will be generally used when you are making HTTP calls or you are doing a file transfer. Okay, so that you can and this data compression will help basically consume less bandwidth and send more amount of information on the wire. Now let's get started with sessions layer. So in the sessions layer, unlike the presentation layer, we do not change the contents of the payload. Rather, we maintain sessions. So we establish new sessions, maintain sessions, we terminate session, and session resumption also happens. So primarily wherein you reuse the older sessions to create new connections. Also, we do cryptographic key exchanges for TLS. So in the presentation layer, we saw that the data encryption happens when we use the symmetric keys to encrypt the data. Now, this symmetric key exchange happens in the sessions layer, wherein you use asymmetric algorithms to exchange keys for TLS handshake. Also, we do file data synchronization. So let's say if you are having a very big file, basically in the sessions layer, you'll be marking checkpoints so that in case if there is any error or corruption of the file happens while uploading or downloading the file, you need not send the whole file all together again, but you will restart only from the last committed checkpoint. Also, sessions layer decide whether the communication is going to be fully duplex, half duplex, or dialog syncs. Like our dialog syncs also is being done by the sessions layer. So what is a fully duplex connection? Let's say you have a client and a server. So in a fully duplex connection, your client as well as the server can communicate at the same given moment of time. Okay, they both can send and receive data at the same given time. Whereas in half duplex connection, only one of the party can send the data at a given moment of time. The other party has to wait. So let's say when client is sending the data, server has to wait and listen, and when server is sending the data, client has to wait and listen. Now, when half duplex connections happen, you have to do dialog syncs, so such that one party has to wait, and that dialog syncs is also facilitated by sessions layer. Okay. Now, one thing we have to keep in mind is sessions layer are logical while TCP connections are physical entities in communication. What do we mean by that? So let's say you type in google.com in your browser for the first time. So what happens? A session is created. Let's call it a session A, and a TCP connection is made. Three-way TCP handshake happens, and a session TLS handshake happens, wherein TLS handshake happens, wherein you're using asymmetric algorithms, your symmetric keys are exchanged so that the whole tunnel is encrypted. Now, let's say you have you are searching for something parallelly. So let's say you have three searches going on: search A, search B. You're searching on Google. Okay, so you're making three concurrent or parallel requests making on google.com. So let's say if you're doing it concurrently, one after the other, so your same session A will be reused. Say when you're doing it for search for B, your session A again will be reused, and when you're doing it for search 3, your session A will again be reused. Now let's assume you're doing it parallelly. So let's say you have three tabs open: tab 1, tab 2, and tab 3, and you are doing searches again parallelly. Okay, so this time, although the searches are parallel, the request would be coming in parallel, but the same session A can be reused, and in the session A, basically your same TCP connection will be used. So a stream would be created. A stream would be created for each of the requests: stream A, stream B, and stream C. So tab A will map to tab 1 will map to stream A, tab 2 will map to stream B, and tab 3 will map to stream C, so that when the response comes, each of the responses go back to their corresponding tabs. So streams are basically, stream IDs are used so that your basically responses are mapped to the correct tab. So we saw that the same session was reused for the requests when we are making connections to the same server. Okay, either concurrently or parallelly. Also, same request, like as in multiple requests, was able to reuse the same session. Now, what happens when your TCP connection tied to a session breaks? So let's say you had a session A, and there was a TCP connection that was made. Okay, now what happens if this TCP connection drops? What happens to the session? So this is where your session resumption comes in play. So if you are using, so this is session resumption is basically governed by your application level protocols. So let's see if you are using HTTPS. Okay, so if this session breaks and a new request comes, if your TCP connection breaks and a new request comes, the same session can be reused. Okay, and a new TCP connection would be made. Let's say this is TCP connection 2, and this will be made, and the same session will be reused. So your three-way handshake anyways happens because it's a new TCP connection, but your TLS handshake was only done partially. You don't have to exchange the whole do the whole asymmetric key exchanges to exchange your symmetric keys. You already have a set of symmetric keys created, so you can just change the symmetric keys, like as in pass the symmetric keys to the servers, and the whole connection is ready again. So you only did a partial TLS handshake. Okay, whereas when you're doing an SSH based communication and your TCP connection breaks, your session is basically not reusable. Okay, so you have to create a new TCP connection and a new session. SSH session is created. A new SSH session is created when you are doing an SSH based communication. Okay, so basically whether your session resumption will happen or not happen depends on your application level protocol, whether that allows that session resumption to happen or not. Okay, so we saw that in this layer mostly it deals with sessions management rather than any modification or any change in the payload of the payload data. Okay, one more thing we can keep in mind is one session always maps to one TCP connection. Okay, in case of HTTP. Okay, one session can map to multiple TCP connections, but only concurrently. So one TCP connection at a time. If this breaks, then second TCP connection, and if this breaks, third, and so on. So multiple TCP connections are tied to one session, but only one at a time, and only when one breaks, the other TCP connections come in play. Whereas one TCP connection is only and only tied to one session at a time. Okay, it cannot be tied to more than one session. Okay, so that's it for this sessions layer. Now we'll start with transport layer. In the transport layer, the connections are established on which the request and the response is sent and received between applications on multiple devices in a reliable or faster manner. So what happens in the transport layer is basically the data that is coming, the payload that is coming from your sessions layer is basically chunked into smaller pieces called segments. Okay, now these segments have a segment header. Okay, and this segment header consists of source port ID, source port, destination port, checksum, as well as the sequence number, the segment sequence number. Now, source port will be used to basically map the response of the particular request, whereas your destination port will be used to map the request to the particular server on the internet. Your checksum is used to check the integrity of the data, whether your data has been corrupted or changed while it was on transit, in transit, whereas your sequence number will be used to maintain the ordering flow. Now, when we are talking about protocols in transport layer, there are primarily two protocols. One is called the TCP and the other one is called the UDP. So the smaller chunked segments, like smaller chunk data parts on TCP layer is called segments, whereas on UDP protocol it's called datagrams. Now if I come around the properties of the TCP as well as the UDP, if I talk about the connection, the TCP connections are connection oriented, whereas UDP is connectionless. What do we mean by that? So when we talk about connection oriented protocols like TCP, the connection metadata are saved. Let's say your sequence number of the connection, or your flow control metadata, or your congestion control metadata. So every connection can be uniquely identified using that metadata in a TCP protocol, whereas in UDP you do not really care about the connection IDs. Okay, so it's like a connectionless protocol wherein you just concerned about the data that is being sent. So you will be concerned about the destination port ID and the source port ID numbers, and you just care about sending the data from the source port ID to the connection port ID, where we don't really care about which connection is being used. When we talk about reliability, so TCP connections guarantee the delivery, so you can make sure that your your segments will be delivered, whereas in UDP the best effort mechanism is used, where your data may or may not be delivered, but the best efforts will be used to deliver, like will be ensured to deliver the data, but it may or may not be delivered. When we talk about ordering, so basically TCP orders guaranteed ordering, wherein let's say if segment 3 arrives before segment 1, so segment 3 will not be rendered to the client directly, it will wait for segment 1, and the whole data will be reconstructed back in the transport layer while it is being received, and then it will be rendered to the client. Whereas in UDP the ordering is not guaranteed, so as and when the datagrams are received, they are rendered back to the client without much care being given to the ordering. So it may be in order or out of order as well. Now because of connection, because of this connection metadata that is saved in TCP, as well as the guaranteed delivery that happens, as well as the guaranteed ordering that happens, the speed becomes slower in TCP, whereas it's the UDP speed is fast. Okay, because of these very reasons. Now when we talk about flow control, so let's understand first what is flow control. Let's say you have a client and you have a server. Now let's say client is downloading some data from the server, and the server is sending data at 10 Mbps, megabits per second. Now if the client is only able to handle data currently at 1 megabit per second, so it can give a feedback to the server that to decrease the speed of the data, and the server can decrease the speed of the data to 1 Mbps, and thus the flow control happens. Okay, so the receiver controls at what speed the sender is going to send the data via this feedback mechanism, which happens in TCP. Similar thing does not happen in UDP, so it does not control the flow of the data. Also there is a concept called congestion control, wherein the server will send the data at, let's say, X megabits per second, and the network itself, the routers and the switches, can give a feedback to the server back that whether they want to speed up the data speed or they want to slow down the data speed, so the networks are not overloaded or underloaded. Okay, so that is what congestion control is. So that again is not allowed in UDP, whereas it is allowed in TCP. Now when we talk about error recovery, in error recovery, basically let's say if the sender is sending some segment to a client, and let's say your checksum, through the help of checksum you come to know that your data is corrupted. So it may the client may ask for the sender to resend the data, the server to resend the data. It also happened that let's say the server has already sent a segment, let's say segment 2, and it has not got the ACK back from the client for segment 2. So in such cases, for timeout of ACKs, where the timeout has happened and the acknowledgement has yet not received by the sender for a particular segment that was sent, that is segment 2, it will try to retransmit this particular segment, that is segment 2. Now this is also a error recovery scenario. Now it might happen that a segment 2 was sent by your server, and client is still sending ACKs for segment 1. A client is not sending the ACK back for segment 2. So if 3 consecutive ACKs have been sent for segment 1, although the server is expecting a ACK for segment 2. So if it is still getting ACKs back from segment 1, it will consider that the segment was lost and it will retransmit the segment, wherein basically here your consecutive ACKs, 3 consecutive ACKs were received for previous segment. So it will try to retransmit the segment once again. Use case, when we come out to when we come about use case, so TCP will be basically used in HTTP while you're web surfing in HTTPS protocols. If you're sending mails, you're using SMTP servers, or if you're using file transfer protocols, SFTP protocols. So everywhere the TCP will be used, wherein your connection needs to be where the segments need to be like delivered. There has to be a guarantee of delivery, and there has to be a guarantee of ordering as well, because the data needs to be come back in order so that it can be reconstructed back. Data can be reconstructed back. Whereas UDP can be used in places wherein you do not really care about if some segments are lost. Example, you are, let's say, video calling and some of the frames were lost, so you don't really care about those frames. Like you can continue doing your video call. Or if like you're doing online gaming, so in online gaming you will make sure that the speed is very fast, and even if some of the data are like as in dropped, it should be okay. And while you're using VoIP calls or audio over internet, so in all these places, even if some data is lost or if the ordering is not guaranteed, it's okay, but we need faster data connections to be there. So that's all about transport layer. Now let's jump into network layer. In the network layer, we do logical addressing, routing of the packets, packet forwarding, and packet fragmentation. So what do we mean by each of them? So let's say the data that you got from the transport layer, that was in form of segments. So along with this segment, the source IP address, that is the IP address of your source computer from where the request is originating, along with your destination IP address, that is your final server's IP address, is appended, and this whole segment is now called a packet along with this information. So this is called logical addressing. Why? Because we are appending the information segments with the IP addresses, which is nothing but temporary in nature. IP addresses are not permanent. So that's why we call it logical addressing. Now these needs to be routed on the internet. So let's say you have a computer, okay, and that is connected to, let's say, one of the LAN networks, which is internally connected to your internet, and which is again connected to one of the networks, let's say, let's call it network A and network B, which is finally having your destination servers. Okay, so let's say that the destination server is having an IP of 192.168.30 and 2, whereas the network is having an IP address of 192.168.30.x. So there will be a mask. So with the help of the mask, we will be able to know the network routes. Okay, so this route, and with the help of the mask, in that once the packet reaches in this particular network, we'll be able to know the host route, okay, which is 192.168.30.2. So with the help of mask and IP address, we'll be able to get to the network, and from the network we'll be able to get to the host, which is inside that network. Now we will also basically be doing the packet forwarding. That is, we'll first we will we'll determine the path. So in packet forwarding, first we'll determine the path, and this path would be determined. This path can be determined through various algorithms, pathfinding algorithms in the network layer. Let's say that we have OSPF, that is open shortest path forward algorithms, or BGP, that is border gateway protocols. So using these algorithms, we'll be able to know the path forward, and we will also be doing packet fragmentation. So let's say if the packets are big and they needs to be fragmented based on your network congestion or the network bandwidth, it will be also done in the network layer. So one packet would be subdivided into multiple packets and then reassembled back in the network layer on the destination side. Okay. Now coming to data link layer. So in the data link layer, basically, once your packet arrives from your network layer, we will be appending the source MAC address and the destination MAC address. And along with this MAC address, now it becomes your frame. Now, why we like we called it as a logical addressing while we were like adding IP addresses in the network layer. We call it physical addressing while we are adding the MAC address in the data link layer, and we call this output as a frame. So the PDU is the frame, protocol data unit. Now, why physical address? Because MAC addresses are physical addresses, they do not change, right? Now this data link layer also does error detection, wherein it uses algorithms to detect errors if there is any error on the frames while it is receiving or sending frames. It also does flow control. So let's say that the sender does not oversaturate or overload the receiver, or it does not just underutilize the network. So it will do the flow control also. It will also do the media control, since the data link layer is now the last layer that is attaching to the physical layers. So this will determine who gets to access the physical layer. Okay. And if some so that like multiple interfaces can use this physical layer, this physical media can be used by multiple interfaces, and they can send the data. So this data link layer will access who gets to send the data on the physical layer. When it will just know that when the physical layer is free, it will just let one of the interface cards push the data while the other interface cards wait. In the physical layer, the data would be sent as zeros and ones. Okay, and this data will be sent in form of a light signal when we are using the optical fibers, and it will be sent in terms of electrical signals when we are using the copper wires, so which is now obsolete nowadays, copper wires. And then it will be sent in terms of electrical waves when you're using Wi-Fi or cellular medias, okay, or radio waves. Now if we take a journey of the data, like right from the network layer to the physical layer, let's see how it all happens in one go. So the data that is leaving on your computer, this is your computer, is basically reaching the router, right? And this router is basically forwarding or hopping your data to the internet. So on your network layer, IP addresses are put on the segments, which we call packets, and then we also put the MAC addresses, which is in the data link layer, called the frames. Now what happens is, from the data link layer, when your data leaves, the source IP is 192, which is of your computer. Okay, the destination IP is of the final device, final servers, okay, which is 8888 in this case. And the source port is basically an ephemeral port, which is 52344, which is bounded to this particular computer again. And then the destination port is 443, which is a standard port for HTTPS. Now for the MAC address, the source MAC address is of this particular computer from where this request is originating, that is, let's say XXYYZZ ABC, A, B, B, and CC, which is like 12 digit alphanumeric character for MAC address. Now what happens is, when this computer tries to send out the data, it sees that the destination IP, which is 8888, is not something that is local to the network. So it has to go through gateways. So what it will do is, it will make an ARP request call, okay, to node the routers, the gateways routers MAC address. Okay, so this ARP request is made to all the devices that is connected on the network, that is the local area network, that is LAN. Okay, so ARP requests are only meant for LAN networks. It's not meant for internet in general. So it will just ask, this ARP request will contain and ask as to who is containing the IP address of the router. So let's say the router's IP address is this, so it needs to know the corresponding MAC address. Let's say if it does not know, so it will just make a call as to who owns this particular IP address. So there will be many devices connected on the local area network. Only the router will respond back to these ARP's request, that is address resolution protocol request, that my IP is being talked about here, and my MAC address is, let's say, AABBCCDDEEFF. So now your segment will contain, your packets will contain the MAC address of the sender and the MAC address of the receivers. Always remember, in data frames, the MAC address is not the MAC address of the final receiver, which is your final, this computer in this case. It is not of the final computer, but it is the next peripheral on which this particular request is hopping to. So MAC addresses are always meant for next hop. So your source computer is MAC address, it already knows its own MAC address, and now through the ARP request it knows the MAC address of the gateway routers. So it will send something like this. So now request is something like this: source IP, source port, destination IP, destination port, source MAC address, and destination MAC address, which is just your next MAC address, not the final destination's MAC address. Now this is filled by the ARP request. Now this, based on this ARP request, it caches this particular MAC address, so that for the subsequent request it may not have to make that ARP request broadcast all over again. And this ARP basically stores the MAC address to IP mapping, because IP was the one which was used to determine what was your routers, based on your router's IP, which we already know as a sender, a gateway router's IP. It will be able to know the MAC address, and that will be cached, and that will be called the ARP store map. Now, what happens inside the router? So now the router has got this particular data. Okay, this data router has got. So what it will do with this data is, now router will basically change the private address, this private IP address, to its own public address. Okay, so this is basically your gateway router's public WAN, which is discoverable on the internet. So on the internet, when the data is flowing, all the public IP addresses has to be mentioned. No private addresses has to be mentioned, because private addresses are not meant for internet. Okay, so what happens is, the gateway router will basically replace this request, this IP and port, along with its own public IP and port. Okay, and it will use its own MAC address now as the source MAC address, and it will make again a WAN ARP request to get the next hop's MAC request. Okay, so using this next hop MAC request, it will be able to send the data forward. Now when the data is coming back, okay, when the data is, let's say the response is coming back, now the response will be having the destination as this particular IP. Now how does the router know that based on this particular IP, who I have to send this response back to? So that will be done with the help of the mapping that was stored in the NAT tables. So when it first replaced the internal IP, private IP, along with its public IP, it will store this public IP, private IP to public IP mapping in a NAT table. Okay, in a NAT table. Now, since there can be multiple requests that can be flowing in, so what it will do, it will also create a PAT table. So NAT table is network address translation table, whereas PAT is port address translation, so that a unique port ID is attached to this particular port. Okay, so based on which particular port the particular request is coming, it will know that which particular private IP to port I'll have to send. So so the NAT will be contained something like this. So let's say if I'm having 192.168.1.10 to 203.10.8.1, and the port would be 52344 to 50001. So if you see here, this is what my NAT mapping would look like. So when the request falls on this would be common for all the requests, because my public IP is not going to change, but this would be unique. Okay, and this would be stored in the PAT table, whereas this would be stored in the NAT table, and with the help of both of them, it will be able to send the exact response to the requested values. So this is how the whole mapping takes place in like internet connected to local LANs where multiple devices are connected. Now, so that's how the data move from application layer to your physical layer, and from physical layer it again will decapsulate, and the data will be basically deserialized, decrypted, and the data will be made in a human readable format so that the application layers can present it back to the network clients, which is your browser and the web apps on which you display the particular data. So that's it for this OSI lecture. We'll meet in the next lecture. Thank you.